So you can see everything, right?
Yes.
Okay, good. Good afternoon, everybody. Thank you very much for the kind introduction. And I truly apologize that I could not travel to Japan. And I really enjoy traveling in Japan, and especially I have really good memories of Kobe and Awajishima Island and all that. So I was really looking forward to it. But anyway, like hopefully I'll get an opportunity to visit this symposium in the coming years. So my today's presentation is about abundant data computing, the next 1000x. This is a project that we are pursuing at Stanford. And before getting into the details of this presentation, I would first like to thank the students, sponsors, and the collaborators. They're the ones that have been doing this incredible work. And I'm really proud to present this work on behalf of all of them. So as part of this next project, the basic concept that we are trying to pursue is this concept of what is called nanosystems to improve computing performance. And when I say performance, I mean the metric, which is energy times execution time. So if we think of that metric, and if you think about how to significantly improve performance, that's where the concept of nanosystems comes into play. So what is a nanosystem? So of course, a nanosystem is built out of nanotechnologies. Now, when we think of nanotechnologies, we have to think about not just new interesting devices, but we have to think about new ways of doing fabrication, new augmented capabilities such as sensors and so on. Now, nanotechnology is very interesting because at one end of the spectrum, you're talking about something really small. On the other end of the spectrum, you're talking about a lot of those really small things. As a result, you have to worry about imperfections, you have to worry about variability, you have to worry about large-scale fabrication, and so on. And when these challenges are overcome, a really important point about nanosystems is that they must enable a new architecture which is not possible with existing technologies. Because if we just simply retrofit existing technologies, existing architectures with new technologies, what you're going to get is, again, the same bottlenecks of existing architectures. So what is really key is that the new nanotechnologies enable new architectures that are not possible using existing technologies. And obviously, these new architectures and these new systems must enable new applications. Now, if we think about applications today, the first most important class of applications that all aspects of computing care about, be it at the edge or be it in the data center or for high performance computing, is what I call abundant data applications, which means that we can collect massive amounts of data and process that data to draw meaningful conclusions. And one aspect of this abundant data applications, which is very important, is what is called the memory wall. Now, on the pie chart that I'm showing on this slide over here, you see that I have not said whether it talks about energy, whether it talks about execution time, because it simply doesn't matter. What really matters is that 95% of the energy or execution time, or essentially the point is a very large chunk of energy and execution time is spent in trying to access the memory, and a very small chunk is goes to the compute itself. Now, many people mistake this by thinking that this is perhaps a limitation of von Neumann machines. But the point I want to make is, it doesn't really matter whether you are doing von Neumann or non-von Neumann. For example, you could have a hardware accelerator, which is non-von Neumann, that would have the same memory wall. And if you look at various kinds of computation models, beyond just our traditional computation models, for example, if you look at brain-inspired computing models, you will see that you have the same challenges about how you integrate computation and memory and how you achieve dense connectivity and so on and so forth. So this is a challenge that we have to address if we have to see significantly improved computing performance. And If you thought that the memory wall was the only wall, that's not the only wall. There are many other walls simultaneously. We already know about the power wall. That's a Dennard scaling that has stopped, now, almost, close to 15 years. And what is really coming up is the, miniaturization wall. Why did I, show these, Russian dolls? Because, this 5 stands for 5 nanometer technology node, which is sort of, what, we have in the world today. And I literally, scaled the numbers. So over here you can see it's, 0.5 nanometer technology node. The question is, are we going to go there? Bottom line is, doesn't really matter where we stop. One thing that's clear is that we have to stop in the next 10 years, which is another very significant wall. So which means that any solution for nano architectures, for nano systems that we build, that must address all these walls simultaneously, right? It must address the memory wall, it must address the miniaturization wall, it must address the power wall, and so on. And this is where our concept of next comes in. But before we get into our concept of next, let's think about what is computation today. If you really think about computing today is pretty boring, because what you got over here is a 2-dimensional chip pretty much, because you've got transistors on the kind of the first layer, and then you have a whole bunch of interconnects, and then you've got this memory chip which is like so far away. And that's where all the energy and execution time are spent, as I was talking about on the previous slide. Now versus when in our next system, what we do is we have layers of compute, we have layers of memory. There's a little problem with the animation somehow on the Let me try to see if I can get out of here, and then let me show you the slide. I think that would be the best.
We can watch the movie very beautifully.
Yeah, but it's not showing up on my screen somehow. Okay, let me try this again. So yeah, in our next nanosystems, we have layers of efficient computing logic, layers of efficient memory. You can even put increased functionality on the upper layer. But if there is one really important point that I want to make out of all this, somehow this movie is, it works very well on real life, okay? Anyway, so if there is one really important point that I want to make over here, it's not just about these layers of efficient computing logic or the layers of efficient memory or the increased functionality. It's the very dense, ultra dense, 3-dimensional. Most important point that I want you to remember. So what we achieve is what we call computation immersed in memory. And this is something that is not possible with business as usual. So let's look at, and by the way, there is like a bunch of papers, especially in the proceedings of the IEEE, special issue in January 2019 that contains the details of our next approach. But let's move into the next level of details of what really constitutes this next concept. So you saw the high-level concept on the previous slide, and on this slide, I'm giving some realization, some implementation of that next concept, right? Now, you have to understand that these are the technologies that we are using to realize the next concept in our lab. There could be other ways of realizing this next architecture that I was showing on the previous slide. So for logic, we use mostly one-dimensional carbon nanotube field effect transistors, but we also look at 2D materials. For memory, we mostly focus on MRAM, the magnetic RAM, and the 3-dimensional resistive RAM, because these two RAM technologies have complementary properties with respect to density, with respect to endurance, with respect to retention, and so on. But a few really important points I want to make. The first one is re-emphasizing that the vertical connectivity between these layers is using ultra-dense and fine-grained interlayer vias, and these are not the through-silicon vias that are generally used for chip stacking. That's the first point. The second point is this structure is fully compatible with existing silicon technologies. That means that they can be built in existing silicon fabs. And the third point is, whenever we think about three-dimensional integration, we always think about, oh my goodness, how do we get the heat out? So these thermal layers that you can see over here. But in the first generation of our architecture, the logic on the upper layers are used for memory accesses. These are mostly used for memory controllers, memory access circuits, and also for the on-chip network. And as a result, because A, memory is cold, B, this is non-volatile memory, so you do not have to keep refreshing this memory. Memory is mostly turned off, and it can be very quickly turned back on. And C, the logic itself is very efficient thanks to the carbon nanotubes. As a result, on the upper layers, you do not need any special thermal solutions for the first generation of our architecture, where the upper layers contain memory and memory access circuits. Now, eventually, when two-dimensional miniaturization stops, that's when you have to go and put heavy-duty compute on the upper layers, because otherwise you would have a logic wall, just like you have got a memory wall today. And under those circumstances, we actually have to go and think of special thermal solutions. But right now, the focus is on the first generation architecture that does not require special thermal solutions. And this forms the basis for a major program. It's close to $100 million, if you consider how much money DARPA is putting in and the cost share and so on. So this is called the 3D SoC program. This is led by Professor Max Schulaker at MIT. He is the PI. And Professor Ananta Chandrakasan from MIT is also a performer. From the Stanford side, it's Professor Philip Wong, Professor Simon Wong, and myself, and Skywater Technology Foundry, which used to be the Cypress fabrication facility. That's the foundry that's part of this program, and Nano-Engineered is a carbon nanotube, supplier. So let's look at, some of the technology aspects. So, for logic, we are implementing carbon nanotube field effect transistors. What are carbon nanotubes? Carbon nanotubes are nanocylinders of graphene with remarkable electrical properties. Typical diameter of carbon nanotubes that we grow in our lab are roughly around 1.2 nanometer. So if you grow carbon nanotubes on a substrate, or if you transfer carbon nanotubes from one substrate to another substrate, and then build, fabricate the source, gate, and drain contacts, what you get is a carbon nanotube field effect transistor, in which along this axis, that is along source, gate, and drain axis, it's lithographically, created. So that's why you are limited by the lithographic pitch. But on the other axis, when you have dense carbon nanotubes, you're not limited by the lithographic pitch. Here is an SEM image of a carbon nanotube field effect transistor. And the carbon nanotubes actually give very significant, a 10x improvement in energy delay product, which I'll talk about later in this presentation. And there has been major progress in fabrication and manufacturing of carbon nanotube circuits, which previously industry thought was impossible. And as a result, as recently as as of last September 2019, from MIT, they actually demonstrated a full RISC V microprocessor using fully complementary full CMOS carbon nanotube field effect transistors. So that's a carbon nanotube story. Now let's look at the story about three-dimensional integration. So when you think of conventional chip stacking, as I was saying earlier, that is achieved using what are called through-silicon vias. Now, what are through-silicon vias? These are these big fat pillars that are shown over here. I liken these through-silicon vias to, the three bridges between San Francisco and Berkeley. And as a result, every time you drive between San Francisco and Berkeley, you're always stuck. Why? Because there are just three bridges. Similarly, if you have the memory city and the logic city, for example, these are, very dense cities thanks to the Moore's law. But if they're connected by the three bridges between San Francisco and Berkeley, as a result, you're always stuck. And that's exactly what's going on with through silicon vias. Instead, what you need is very dense vertical connectivity. And now if you think about what is the densest vertical connectivity known to humankind, those are the vertical back-end of line vias that are already existing in today's silicon chips for connecting the wires on various layers. Now, that would mean that, why don't we go and try to put transistors and memory cells on various layers of our, integrated circuit chip that's, available today? That would be called monolithic three-dimensional integration. Now, this is something that is impossible with existing silicon technologies, because to build a silicon transistor, it requires a very high temperature of around 1,000 degrees C. And if you try to build something at 1,000 degrees C on an upper layer, everything underneath that you built would be damaged or very, very severely. And as a result, you cannot actually build this monolithic three-dimensional integration using silicon transistors. Fortunately, the emerging logic technologies, for example, carbon nanotube transistors, or in emerging memory technologies, for example, RRAM and MRAM, they can be naturally built at less than 400 degrees C, which is, kind of is the limit of the temperature of processing on the upper layers. And as a result, in addition to providing their own benefits, in addition to providing the basic benefit of using carbon nanotubes and so on, you can actually now realize this monolithic 3D architecture of this various logic layers and various memory layers with very dense vertical connectivity, kind of a next architecture. So you can combine device and architecture benefits that are very difficult, if not possible, using existing silicon technologies. Now, I talked about carbon nanotubes. I talked about 3D integration. Now let me spend a little time talking about advances in resistive RAM. So, for example, at ISSCC last year around this time, we demonstrated that if you use resistive RAM as a technology, you get, close to 30x lower active energy compared to chips with embedded flash, for example, right? So that's a very significant improvement. Apples to apples, these are actually hardware comparisons. Similarly, we know that these non-volatile technologies are, have endurance issues, which means that you can only store very few bits, you can only write very few times, over lifetime of a system. And we have been able to demonstrate, very good, lifetime for machine learning applications. And also I'll touch upon this multiple bits per cell on the next few slides. Now, if you look at this multiple bits per cell, since there is an insatiable need for on-chip memory, as I was talking about earlier in the context of the memory wall, the question is, given a certain amount of memory, how can we actually increase the effective number of bits in the memory, which would mean to store multiple bits per cell with resistive RAM technology. Now, while previous work showed that in kind of, standalone cherry-picked at a single cell level, you agree that unless this can be demonstrated at full arrays, it's useless. And thanks to our work on new ways of programming resistive RAM, we have been able to achieve, 3 bits per cell at full array level. And at ISSCC last year, we were able to actually demonstrate that how you actually, encode the weights in neural nets so that any variability that's associated with this multiple bit per cell storage is kind of overcome in a resilient way. So as a result, on the same hardware, you can feed bigger neural nets, and as a result, you can get highly accurate inference that has been measured. Earlier, I already mentioned the endurance challenges of non-volatile memory technologies such as resistive RAM and flash and so on. Now, which would mean that you could have only very few writes over system lifetime in general. But what we have been able to demonstrate, thanks to a new technique called endurer, which I won't have the time to get into the details of, and that's enabled by the byte addressability or byte accessibility of resistive RAM, we could actually show that you could actually run 10 years of continuous inference in an actual system that's shown over here, which was is a non-volatile IoT microcontroller, for example. And with this technology, we were able to show like a continuous operation with very high degrees of inference accuracy, for example, using this endurer technique, despite limited endurance of the non-volatile memory technology. And if you were wondering that are these things just some things that the Stanford folks are doing in their lab, or is this something really real? So of course we did a lot of demonstrations both at Stanford and at MIT at a lab level, but we are very proud to announce that now these things are moving to the fab, and at the DARPA ERI summit that was held in July of 2019. That's where our team actually demonstrated. Actually, we brought a full wafer. This is actually Professor Max Schulacker from MIT, and he actually brought the first full wafer from Skywater Technology Foundry, which is a silicon foundry, right? A conventional commercial silicon foundry, to show that this monolithic three-dimensional integration of CNFET and RRAM is realizable, at a full wafer scale, in an actual silicon foundry. So for the rest of this presentation, since the theme of this session is co-design, let's look at, given this theme of, next, how co-design fits in. And we will go through various layers of abstraction before I end my presentation. First, let's look at, how at a device level and a circuit level, you can do interesting co-design to enable interesting things. So first of all, I was talking about carbon nanotube field effect transistors, right? And I kind of explained what carbon nanotube field effect transistors were at a high level. The immediate question is, what benefits do carbon nanotube field effect transistors bring, not at an inverter level, not at a transistor level, not at a NAND gate level, but at a full processor level, for example. And here is this joint work with IMEC and TSMC that we did. And we were able to show that, and what's shown on this slide is that the y-axis is energy, the x-axis is frequency. So you want to be running at a very low energy, but at a very high frequency. So if you look at FinFET or the nanowire field effect transistors, which is is the next generation of transistor technology, you see that the benefits are very small. Versus with carbon nanotube field effect transistors, you see enormous benefits, an order of magnitude improvement in energy delay product at a full digital system level. And I won't have the time to get into all the details, but if you read our paper, you will see that, we answered a variety of frequently asked questions that people generally ask us. And I love this one especially. Don't wires limit performance? Why are you researching FETs? Well, because when you improve a FET, the wires improve as well very significantly. And if you are a designer type, actually there is a nanosystem design kit that we actually created to enable this carbon nanotube technology that you can play with. So now that I kind of talked about circuit and device level interactions as part of co-design, let me say a few words about going from circuits through architecture through a system with a very few chips, right? And that's where what's very important is beyond the specific technologies that I presented. As you saw, that so far as our fabrication in the Skywater Foundry is concerned, we are mostly looking at carbon nanotube field effect transistors, resistive RAM, magnetic RAM, and monolithic, ultra dense monolithic 3D integration. But what is equally important is to understand there is a whole vast variety of heterogeneous nanotechnologies, and what impact would they have at an overall system level. So you co-explore technology, architecture, and application. And one of my former postdocs, now a professor in Singapore, Professor Mohammed Sabri Ali, he actually created this next simulation framework where on one end of the spectrum, we take into account all these heterogeneous nanotechnologies. On the other end of the spectrum, we look at abundant data applications. For example, we support TensorFlow, which is Google's framework for machine learning, for example. And we can perform system level analysis We can explore architectures and their trade-offs with respect to energy, execution time, thermal, and so on. And oh, by the way, we have a set of EDA tools that can actually do a physical design of that whole next architecture in 3D and so on, so that we can go and extract the capacitances and everything and are very accurate so that we know that these architectures are actually routable. And when you look at a wide variety of applications, not just neural nets, you look at graph analytics, you look at conventional machine learning and of course deep learning, you see that you get very significant benefits at the level of 1000x using existing software, which is extremely important because, as you know very well, trying to rewrite software is very hard. And the simulation framework that I was showing before, it is useful in many ways. It's useful for quantifying the benefits of a certain set of technologies. For example, for the technologies that we are looking at in the context of NEXT, I showed you earlier that they give very significant benefits with respect to the energy execution time product metric, close to 1000x, which is a kind of a really good metric for computing performance. But at the same time, that kind of a simulation framework also allows us to derive new technology targets. For example, over here you see that, why is vertical connectivity so important? So if you sweep the amount of, like the pitch of kind of, vertical vias, you see that when you have a pitch of around 5 micron, which is, by the way, smaller than conventional TSVs, which has a pitch of 10 micron, you actually get only an 8x benefit. And, out of this 8x benefit, for example, in energy delay product, a significant chunk is coming from carbon nanotubes. So if you had a silicon technology and then you had, a lot of, just vertical TSVs, you can get very small benefits of, roughly around a 2x or a 3x. And that makes you wonder that is it worth paying all this money for such small benefits? So deriving these technology targets and understanding why, you need, for example, very dense vertical connectivity is very important. Another example of, this similar, circuit architecture and small scale systems is this resilience aspect that I was mentioning before in the context of Enduro. So for example, if you use flash inspired wire leveling techniques for resistive RAM, you will see that you are stuck in this region where you will need a lot of extra SRAM beyond the resistive RAM that you need, right? Because you have to store all these tables and all that. And you can see that the lifetime that you achieve is not that high. Versus with Endurer, this is the preferred corner because you want to have very little extra SRAM and you want to have very long lifetime. Endurer can achieve something like that. Another example of co-design that takes into account the technology aspects, because this is byte addressable resistive RAM, and then interesting design and architecture techniques to kind of achieve such high degrees of resilience. And so far as many chip systems are concerned, in that context, you could think about, hey, how about an HPC system, high performance computing system with many next nodes. This is where we are collaborating with our collaborators at the Lawrence Berkeley Labs and the Lawrence Oak Ridge National Labs. We are actually creating a larger scale simulation framework to understand what benefits this can bring to HPC systems and to the cloud. And there are many more co-design opportunities which I didn't get a chance to talk about. For example, as I said, when two-dimensional miniaturization stops, you have to put dense compute on the upper layers, and then what kind of thermal solutions one needs to think about. Or new software optimizations. The numbers that I showed you earlier was with existing software. But now that we have a next technology with a next architecture that enables new software optimizations, which opens up new opportunities for exploration. So to conclude this presentation, I would like to say that nanosystems can be achieved today, and it's a nanosystem, not just a nanotechnology. And I talked about the lab to fab effort, and for example, the carbon nanotube field effect transistors, resistive RAM, and monolithic 3D. They're actually working in an actual silicon fab today. I showed you that the next concept can enable massive benefits with existing software for a wide range of applications, and there are many cross-layer co-design opportunities that we as a community can think about moving forward. So thank you very much for your attention, and I'll be glad to take questions.